Welcome to the Sheyas, your map.
Hi friends, today we are going to discuss point of inflection. Let us discuss the point of inflection in the graph first. Okay, now see this graph. This is quadratic graph. These two are quadratic graphs. This is cubic graph and this is biquadratic or quartic graph. Okay. In this quadratic graph, the graph is upwards. That is, the concavity is upwards. And here, there is no change of direction. So, we can conclude that this graph has no point of inflection. And just see in the inverted U-shaped graph, the concavity is downwards. And there is no change of concavity or no change of direction. So, here also there is no point of inflection. Just see in this cubic graph, so this is concave down, okay, and in this is concave upwards. So this is concave down and this is concave upwards. So here occurs a change of direction. So this change of direction occurs at this point and we call this point as point of inflection. See, this change is not here. It's just concave upwards and this is concave downwards. But see this graph. This is concave downwards and concave upwards. So this change of concavity, this change of direction at this point is called the point of inflection. Now see here, in this cubic graph, so this graph is again concave upwards. This side is concave upwards and this side is concave downwards. And so we call this point as point of inflection. Okay, now see in this is also a cubic graph. So in this graph, this is upwards and this is downwards, concave downwards. And so the change of direction, the point where the graph changes its direction. So this point, see here where the graph changes its direction is point of inflection. Again in this is downwards and here also it is, and here it is upwards, concave upwards. And this change of direction at this point we call it as point of inflection. So in quadratic graph we don't have point of inflection and in cubic graph these are the point of inflection. Okay, now let us discuss the point of inflection in biquadratic or quartic function. This biquadratic graph or biquadratic function can also be called as quartic graph or quartic function. Just say this. So here the concavity is downwards and again this side the concavity is downwards. Here the concavity is upwards. The concavity is upwards. So this change of this at the point where the change of direction, occurs, where the concavity changes, we call this as point of inflection And just see here, here also, because it is downwards, then it changes to upwards. So this point where the concavity changes or where the graph changes its direction, we call this point as point of inflection. So today we are going to solve problem using cubic graph. Okay. So one more thing I want to say is, so this is the cubic function y is equal to x cube plus bx square plus cx plus d. So if a graph has local maximum, local minimum, the graph will be like this. Okay. So if a is greater than 0, that is a is positive, a is greater than 0, then the graph will be this shape. And if a is less than 0, that is negative, if a is some negative value, that is a less than 0, then the graph looks like this shape. So same for this also. If a greater than 0 in the cubic function, if a greater than 0, then the graph will be this shape. So this graph has no local maxima, no local minima. And this graph also, the same thing, it has no local maximum, local minimum. If a less than 0, the shape will be this side. Okay, the shape will look like this. So before solving the problem, we have to understand some of the points. An inflection point is a point on the graph of a function at which the concavity changes. So we have seen these things in the graph. So points of inflection can occur where the second derivative is 0. So to find points of inflection, what you have to do? You have to put the second derivative 0, and that x value will be the x coordinate of the inflection point. You will clearly understand when solving the problem. If the cube, some more points we have to recall. We have to understand some more points. That is, if the cubic function has only one stationary point, this will be a point of inflection. That is also a stationary point. Okay. So if the cubic function has only one stationary point, then that one stationary point will be the point of inflection. Okay. And based on this, we'll do one problem. And based on the second information also, we'll be doing another problem. Okay. For points of inflection that are not stationary points, find the second derivative and equate it to 0 and solve for x. So here, if the stationary points are not points of inflection, then what you have to do? You have to put the second derivative 0 and find the point of inflection. Okay. So when doing problems, you will understand more. And the last point is, if the function has two stationary points, establish whether they are maximum or minimum turning points referring to the shape. So if the function has two stationary points, then what you have to do? You have to confirm whether those 2 points are maximum, that is local maximum or local minimum. So now we are going to solve one problem under the topic point of inflection. By considering the gradient on either side of the stationary points on the curve y is equal to x cube minus 3x square plus 3x, show that this point is a point of inflection. Sketch the curve y is equal to x cube minus 3x square plus 3x. So given the function is y is equal to x cube minus 3x square plus 3x. Now you have to show the point of inflection. Okay, first let us find the point of inflection. Okay. First you have to differentiate it, dy by dx. So once if you differentiate, x cube differentiation is 3x square, then minus 3x square differentiation is 6x. Then 3x differentiation is 3. So now to find the stationary points, what you have to do? You have to put the first derivative 0. That is, the first derivative 0 you have to put is equal to 0. So 3x square minus 6x plus 3 is equal to 0. Now from these two, I am taking 3 outside. So x square minus 2x plus 1 is equal to 0. So if I factorize this, I'll be getting x minus 1 and x minus 1. That is x minus 1 the whole square is equal to, if you apply a minus b the whole square formula, you'll be getting a square minus 2ab plus b square. So when I factorize this, I'll get the value x minus 1 and again x minus 1, which is equal to 0. So two values you are getting, that is both are same, x is equal to 1 and x is equal to 1. So here you are getting only one stationary point, that is 1. So the stationary point will be, so you have got the x coordinate of the stationary point. Now you have to substitute this x is equal to 1 in the y is equal to x cube minus 3x square, because you have to get the y coordinate also. So once if you substitute, what will you get? 1 cube minus 3 into 1 square plus 3 into 1. So 1 minus 3 plus 3, that is nothing but 1. So y is equal to 1 you will get. So if x is equal to 1, you are getting y is equal to 1. So 1 comma 1 is a stationary point. One comma 1 is a stationary point. So you have got again 1. So when you do the same, you will be getting the same point again. So you can just write 1 comma 1 is a stationary point. So we have got the stationary points and only one stationary point we have got. And now let us find the second derivative. So what is the first derivative value? 3x square minus 6x plus 3. Now we have to differentiate again to find the second derivative. So when you differentiate, it will be 6x minus 6. Okay. So what is the stationary point you obtained? 1 comma 1 is the stationary point what you obtained. So this stationary point, that is 1 we have to, that is x coordinate you have to substitute in the second derivative. So when x is equal to 1, just see what the second derivative value will become. So x value is, that is you are applying the stationary point in the second derivative to find the nature of the stationary point. So when you apply that, when you apply the stationary point, x value is 1 minus 6. So you are getting 0. So d square y by dx square is 0. So the second derivative is 0. So how can you conclude? You can conclude this 1 comma 1 is a point of inflection. So you are getting the value 0, so that you can conclude this point is a point of inflection. So this stationary point, here only one stationary point you got, and that stationary point is a point of inflection. So once again I will remind you the condition. See, to find the point of inflection, we have to get this f double dash of x is equal to 0. So that will be the inflection point. Okay, from that you will get the x coordinate of the inflection point. Okay, so according to that condition, what we have got, so the second derivative is 0, that is nothing but f dash of x. Okay, the second derivative is f double dash of x. F double dash of x, that is second derivative, 0 you are getting. So that point x is equal to 1 and the corresponding point is 1 comma 1. So that point is the point of inflection. So now we are going to sketch the graph of the function y is equal to x cube minus 3x square plus 3x using the point of inflection. So see here, when solving the problem, what are all the things we have got? 1 comma 1 is a point of inflection. From the problem, what we understood, that is we didn't get any local maximum or local minimum points. We only got point of inflection. Okay. Okay, now we are going to sketch the graph. So before that, we have to understand some more points. So the graph given is a cubic function because the highest power is 3 and so it is a cubic function, x cube minus 3x square plus 3x. So this is of the form y is equal to ax cube plus bx square plus cx plus d. So if it is a cubic function, these 4 graphs are the possibilities. Among these we have to confirm which graph is in our problem. Okay, which is the correct graph of this given function. Okay, so in our problem what we have solved, we didn't get local maximum or local minimum points, but these 2 graphs are with local minimum and local maximum points. But the problem what we have solved, we didn't get local maximum or local minimum, so these 2 graphs won't come. The possibilities are these 2. So just see here, if A is positive, then the graph will be this shaped, and if A is negative, the graph will be on the other side. Okay, so here A is positive, that is A is 1, so A is greater than 0, so your graph should look like this way. Okay, so this is the shape of the graph in your problem, in the problem what we are solving now. Okay, so this is the shape of the graph, because this graph has no local maximum and no local minimum points, and it has point of inflection, and this A is equal to 1, and it is the positive value, and that A is equal to 1 is greater than 0. So this graph will be your required graph. Okay, so let us do that in our problem. Let us sketch that. Okay, now 1, 1 is a point of inflection. So just mark that point. 1, 1 is a point of inflection. So this is the point 1, 1. Now we are going to draw the graph. So this graph has no local maximum, no local minimum, and just a point of inflection. So we have to, so point of inflection, this is, it changes direction. So already we know how the shape will be. And you have to draw the graph this way. So we have sketched the graph of y is equal to x cube minus 3x square plus 3x using the point of inflection. So the same problem, once again I repeat. So what is the question? By considering the gradient on the either side of the stationary points on the curve, we have to prove that that point is a point of inflection. Okay, so we have sketched the graph also. So what we have done, we have considered the gradient and we have found the stationary points. Okay, and we have proved that this point is a point of inflection by finding f double dash of x 0. Okay, and we have concluded that this 1, 1 is a point of inflection, and then we have sketched the graph. Now let us discuss the next problem. So next problem, again we are considering the cubic graph. Okay, that is cubic function y is equal to x cube minus 27x. So see, in this problem, first we are finding the stationary points. Okay, so to find the stationary points, we have to put dy by dx is equal to 0. So what is dy by dx? 3x square minus 27, that is 0, and 3 we are taking outside, so x square minus 9. So just see here, this 9 can be written as 3 square, and this is of the form a square minus b square. So the formula is a plus b, a minus b. So I'll write that, a square minus b square, the formula is a plus b into a minus b. So that's how I have written I have factorized, or you can directly factorize using calculator also. So from this you got two values, x is equal to 3 and x is equal to minus 3. Okay. Then what you have to do is, you have got the x coordinates, that is you have to find the y coordinates of the stationary points. Okay. So here when x is equal to 3, you are getting y value, that is in the function y is equal to x cube minus 27x, you have to substitute this 3, and so you will get y is equal to 3 cube minus 27 into 3 and y is equal to minus 54. So 3 comma minus 54 is a stationary point. And again when x is equal, because you have another point also, when x is equal to minus 3, you have to substitute in y in the function. So you will be getting y is equal to 54. So minus 3 comma 54 is a stationary point. So what are all the stationary points obtained? 3 comma minus 54 and minus 3 comma 54 you have got two stationary points. Okay. So now you have got the stationary points. The next step is you have to find the second derivative to confirm the nature of the stationary points. Okay. So the first derivative, what we have got is 3x square minus 27. Now the second step is you have to find the second derivative. So when you differentiate again, you will be getting 6x. So one stationary point is 3 comma minus 54. So this stationary point you are substituting in the second derivative, that is d square y by dx square. So in the place of x you are getting 3, you are substituting 3. So you will get 18, which is greater than 0. So if the second derivative value is greater than 0, then we can conclude that it is local minimum, and that point 3 comma minus 54 is a local minimum point. And see, the same thing we have got one more stationary point, that is minus 3 comma 54. So that value we are again substituting in the second derivative to confirm the nature of the stationary point. So when you substitute x is equal to minus 3, you will get minus 18. And that value, the second derivative value, that is d square y by dx square, you are getting it as minus 18, which is less than 0, and that is local maximum. According to the condition, we can decide that it is a local maximum value. And so minus 3 comma 54 is a local maximum point. So here what we have concluded is, in this problem we have got two stationary points, and those two stationary points, one is local minimum point and another is local maximum point, but we didn't get any point of inflection. Okay. So now we are going to sketch the graph. So what is the function? Y is equal to x cube minus 27x. What are all the things we have got? 3 comma minus 54 is the local minimum point, and minus 3 comma 54 is the local maximum point. And these are the points we have obtained from the problem. Okay. Now using all this, you are going to sketch the graph. So here, where is the point minus 3 comma 54? Minus 3 comma 54. So I have taken the y axis as 10 units because you have 54 here. So in order to make the graph clear, I have taken y axis 10 units. 10, 20, 30, minus 10, minus 20, minus 30, and x axis as 1 unit. 1, 2, 3, like that. Now, where is the point 3 comma minus 54? Minus 3 and 54. 50 above we have 54 and minus 3. So this is the point minus 3 comma 54. Okay. And 3 comma minus 54, here 3 and 54. Minus 54 is here. So 3 comma minus 54 is the local minimum point, and this is the local maximum point. So the graph has local maximum and local minimum point. Now see here, the graph should be in any one of this form, okay, because it is a cubic function. And here you see x cube minus 27x. So this is of the form ax cube plus bx square plus cx plus d. Okay. So the highest power is 3, and this is of the form ax cube plus bx square plus cx plus d. Now here a is 1, and that is 1 is nothing but greater than 0, and this graph has local maximum, local minimum point. Since it has local maximum, local minimum point, we have to choose any one of this. This won't come. So when we are choosing this, we know that a is greater than 0, that is a is 1 here and it is greater than 0. So we have our graph looks like this way. Okay. So our graph looks like this because a greater than 0 and 1 is greater than 0, and it has local maximum, local minimum point. So with these points we can sketch the graph. So how our graph looks like this way. Okay. So I'm joining these points, concave downwards and then concave upwards. So thus we have sketched the graph of this cubic function y is equal to x cube minus 27x with local maximum, local minimum points. Okay. So in this problem, we have got two stationary points, and that two stationary points are, that is, one is local maximum, local minimum point. We didn't get any inflection points. Okay. These points we have seen in the introduction part, but once again we can repeat this. See here, if the cubic function has only one stationary point, this will be a point of inflection, that is also a stationary point. The first problem what we have done, in that we got a stationary point and that point is a point of inflection. Okay. Now in this problem, see this point, for points of inflection that are not stationary points, find the second derivative and equate it to 0. If the function has two stationary points, establish whether they are maximum or minimum turning points referring to the shape. So here in the second problem, we have got two stationary points and we have found the nature of the stationary points also, that is maximum or minimum. So we have got one local maximum point and one local minimum point in the second problem, but we didn't get any inflection points. So how to find the inflection points? For points of inflection that are not stationary points, find the second derivative and equate it to 0 and solve for x. So you have to find the second derivative and you have to equate it to 0. So what is our second derivative? D square y by dx square is equal to 6x. And according to the condition, what we have to do to find the points of inflection? We have to put this second derivative to 0. That is, we are finding the point of inflection. So 6x is equal to 0. So x is equal to 0. So we have got the value x is equal to 0. Now you have to apply this 0 in the y value. So what happens? Y is equal to 0 minus 27 into 0, that is nothing but 0. So what we have done, we didn't get any point of inflection from the stationary point. So according to the condition, what we did, we have equated the second derivative to 0 and what we have solved for x, and the x what we have got is the x coordinate of the point of inflection, and we have substituted in y to get the y coordinate, and so we are concluding that 0, 0 is the point of inflection. And just see in our graph, so this is the point of inflection. Just see in this graph, 0, 0 is the point of inflection. So this is the 0, 0 and this is the point of inflection, which means that the change of direction, the concavity changes. Here it is concave downwards and here it is concave upwards. So 0, 0 is the point of inflection and we have sketched the graph also. If you have any doubt, you can post it in the comment box. And thank you.
Thanks for watching. Like and comment. Please to subscribe to our channel.